A very important statement regarding cross-section balancing is that geologically reasonable cross-sections must honor or must satisfy or must fulfill the structural style of the region. A cross-section that follows this is known as admissible. A balanced cross-section must be admissible. What does it mean? Suppose in a simplified diagram, I understand that below the earth surface there is kink fold, or on the surface we find good evidence of kinking during field work. This means that if I extrapolate a fold on the ground surface, or if I extrapolate a fold below the ground surface, it should be kink fold only of same style. And when I create a cross section, this structural style over here and what I am thinking below the surface, or conversely the known structural style here and what I am thinking here, which now has been eroded, should all come in the cross section. It will be a wrong cross section if I am thinking round hinge fold, whereas in reality there are smaller kink folds. Taking an example of a fault, suppose we are dealing with an extensional terrain, our tendency should be to fit normal fault. We should not bring reverse fault easily, but in case after putting normal faults we are not able to explain, then reverse faults can be thought about within the cross section. Let us explain this portion in simple language. Take the case of the Himalaya, the Pakistan sector, the Indian sector and the Myanmar sector. Suppose this is a transect. Most of the Himalayan rivers are taking many turns, but overall they are flowing in this direction, except the mighty Brahmaputra that grows in the Tibetan region for thousands of kilometers along the Himalayan track. Now, here suppose you are looking at a vertical section created by a river. This is the geographic northeast direction, this is the southwest direction, and in vertical cross section, suppose this is your real observation in the field. We are finding disrupted units. Clearly we understand this is a fault. Here there is vegetation, and consider here the rocks are not exposed, or a man-made wall is created to stop the landslide. Now, what should I interpret? Should I call it a normal fault or a reverse fault? This is a situation when there is no marker unit. The layer in the footwall block or the layer in the hanging wall block are not distinct and unique, so that we are unable to say which layer moved up or which layer moved down. What is the structural style of the region? Himalaya, we know 55 million year onward till present is undergoing compression. The mountain is still moving up. From other source of information, this is what we know. So, the structural style of the region is compressional. There are strike slip faults also, but first order information is that the Himalayan mountain is a compressional orogeny. So, here instead of normal fault and where the marker units are lacking, our tendency can be to fit a reverse fault. That means, suppose this is a marker and here is a marker, then we can see that there is a movement. Our tendency here will be to fit or think about reverse fault. Having said this, be very clear that in compressional orogens such as in Alps, in the Himalaya, there are extensional normal faults present that leads to debate and intense research. How come extension is possible for a geological time range within the compressional orogen? So, when we say structural style of the region, the first statement is look at the existing literature and find out what is the deformation regime. At the same time, if you find too many examples of real normal faults in the Himalaya, simplified diagram, then we cannot ignore, and in that case actually the structural style of the region needs to be revised. We rely on existing information, but we cannot rely blindly on the existing information. Creation of cross section is important, and we have to keep our eyes open and ready to reinterpret in case our observation, this kind of observation is repeatedly found in the collisional orogeny, where a marker unit can clearly be seen and its disruption is indicating a normal fault. So, in that case the structural style of the region needs to be revised. To balance a cross section, it must be restorable. In other words, it should be retro-deformable. This means that there should be no gap or overlap after balancing the section. Any two pieces of material cannot simultaneously occur the same space. If someone is balancing a cross section and is creating a situation where the two layers overlap at the same time range, that means something has gone wrong. At the same time, a deformed layer after restoration, if turns out to be like this, where there is gap is also not permitted, which means that there is a wrong balancing. So, there should not be any gap, there should not be any overlap. If we avoid overlaps and gaps, the kind of cross section is known as restorable or retro-deformable. Retro-deformation is known also as the palinspatic reconstruction. A cross section that can be restored to a reasonable pre-deformational condition is known as viable. That means, if with gaps or overlaps the cross section is, the balancing is not viable, and the balanced cross section must be both admissible and viable. Viability is explained here, and the meaning of the term admissible I have explained here. Interestingly, there can be more than one viable solutions for the same data set. If this is the final product, we can think of deformed rock, which is the final material, nature's creation, can come from two possible viable solutions V1 and V2. Therefore, if V1 is working, V1 is not the actual situation in the past, there can be other possibilities as well. The term gap and overlap is explained in this cross section balancing. This is a case where here is a flat, there is a ramp, and then there is a flat. A reverse faulting has happened. The hanging wall block has climbed up towards the foreland side, and that side is the hinterland side. This is layer 1, and we can see layer 1 has climbed over here, and this is layer 2, which has also climbed up. Suppose a restoration is done where layer 2 is presented and here is layer 1 continuing, but unfortunately there is an overlap of 14 millimeter of layer 2. That means this cross section is wrong. Or there is another way of reconstruction where we find that there is a gap in layer 1 of equal length. This length is 14 millimeter. This is also an impossible situation. So, these two situations are to be avoided. We need to understand two terms that are used in cross section balancing. I will also be using soon: pin line and loose line. Consider there is a folded layer. To perform the cross section balancing, I want to choose a place where the cross section balancing will be specified. To do that, I locate a place where the undeformed rock. Why this portion is undeformed? Because this is not folded and this is horizontal and straight, that meets the deformed material. This is the undeformed part, this is the deformed part. Where they meet, I can draw a line like this and consider a pin. We call it as the pin line. The second pin I can think here. Now, within these two pin line I can focus. Since this portion is undeformed, this portion is also undeformed, they will be ignored and our study will be only between the two pin lines. Also note how the pin lines are set. This pin line is perpendicular to the bedding plane, and here bedding plane in the undeformed rock portion, and here also the same thing. Now, you can argue what will happen if the pin lines are chosen differently. Say this is a folded layer, very simplified diagram, and instead of choosing here, I choose the pin line here and over there. In that case, not much change will happen in the cross section balancing, but you are unnecessarily adding up this much of area which is already undeformed. where no restoration is required. When I demonstrate with paper and pen a cross section balancing and two pin lines, you can choose the pin lines a little bit away from the deformed body and try and see the same results will come out. Now, out of these two pin lines, sometimes we consider one is static and we are going to move this pin line for restoration. A folded layer is essentially produced by compression. So, this pin before deformation might have been somewhere here, right. This might be the layer, and on compression that line has come here. The pin that is moving can be called as the loose line. Now, here in the diagram, students can ask a question, why did I choose the left pin line as static and the right pin line as a movable? The answer is you can choose any one of them as the static one, the pin line, and the other one as the loose line. If this is my choice, then how the restoration can be thought about? This one is static. Suppose this folded layer is opened up, then here is the loose line. This is the undeformed situation and this is the deformed situation. Our results will not vary. So, any one of the pin line can be considered as the loose line. As you see in my diagram, the angular relationship between pin line and the undeformed layer is 90 degree. That one is maintained in the before deformation situation. So, also here this was a loose line making 90 degree with the bedding plane after deformation, and before deformation case also this angle is 90 degree. This has to be maintained if you are making a proper cross section balancing. Let us look at this situation of thrust belt. Here is a flat, here is a ramp, and then again a flat, then ramp, then flat, and then a ramp. In this direction tectonic transport is taking place. Suppose we want to restore this section, then we can choose this as the pin line. This is the loose line. That means this we can move in that direction. Thrust belts are also produced due to compression. That means after compression the loose line has come here, which means before compression the loose line has to move in this direction. Suppose a restoration is done and we find that the loose line is showing this kind of geometry. This kind of geometry of the loose line indicates that there must be some mistake, and this is not taken as the correct cross section balancing. When I demonstrate the loose line movement, you will find that the angular relationship between the loose line and the bedding plane after deformation and before deformation remain the same. Here that one has been violated. What is backstripping? This term comes in cross section balancing. It is a kind of isostatic restoration where the focus is on the subsidence history of a basin by successively removing sedimentary sequences and balancing isostasy. Can be explained with a simple diagram. Suppose this is a sedimentary basin and then there are sediments that got deposited. As sedimentation happened, the basin underwent sagging. The basin got sagged. So, this line A0, B0 might have come over here as A1, B1. As a result of that, each layer also underwent movement downward. In the process of backstripping, we tend to think, what if this layer of sediment is removed? Once this is done, successively the next layer will also be removed. Say this layer, second layer also got removed. In that case, the sagged basin would have moved upward, and this is known as backstripping.